Dear learners, we are beginning a new course, Quantum Chemistry. In the first module, we are discussing an introduction to quantum mechanics. This module contains discussion on classical mechanics and its limitations, need of quantum mechanics, historical timeline of quantum mechanics, the black body radiation, Planck's quantum theory of radiation and the radiation law. First of all, quantum mechanics. The term quantum mechanics was first coined by Max Born in the year 1924. Quantum mechanics is a physical science dealing with the behavior of matter and energy on the scale of atoms and subatomic particles or waves. The acceptance of quantum mechanics is due to its accurate prediction of physical behavior of systems, including systems where classical mechanics fails. That is, quantum mechanics can explain several phenomena that cannot be explained on the basis of classical mechanics. Now, classical mechanics. Classical mechanics is important as it gives the foundation for most of physics. Classical mechanics deals with the question of how an object moves when it is subjected to various forces, and also with the question of what force acting on an object which is not moving. The theory, the classical mechanics, is purely based on Newton's laws of motion. It provides essentially an exact description of almost all macroscopic phenomena. That is, classical mechanics can explain majority of macroscopic phenomena. Classical mechanics is sometimes referred as Newtonian mechanics since it lies on Newton's laws of motion. Now, we are discussing limitations of classical mechanics. It should be noted that there are several limitations for classical mechanics. As far as the microscopic properties are concerned, the limitations are very much. And in the present discussion, we are focusing on various limitations of classical mechanics. First of all, the classical mechanics fails to explain the spectrum of black body radiation. What do you mean by the term a black body? A black body is a perfect emitter and a perfect absorber of all radiations falling on it. The radiation emitted from the black body depends on the temperature at which the black body is placed. The temperature dependence of black body emission cannot be explained on the basis of classical mechanics. Now, the classical mechanics fails to explain discrete atomic spectrum. What do you mean by atomic spectrum? The spectra shown by atoms is known as atomic spectrum. You are familiar with the emission spectrum of hydrogen and different series in the emission spectrum of hydrogen like Lyman, Balmer, Paschen, Brackett, Pfund and Humphrey series. The existence of atomic spectrum cannot be explained on the basis of classical mechanics. Hence, it is another limitation of classical mechanics. Next limitation is its failure in providing an explanation to photoelectric effect. We know that during the falling of radiations of suitable frequency on certain metals, electrons will be ejected from the metal surface. This phenomenon is known as photoelectric effect. The classical mechanics cannot explain the photoelectric effect. Now, the pair formation is another phenomena that also cannot be explained on the basis of classical mechanics. What is meant by pair production or pair formation? When photons or radiations of suitable energy is allowed to fall under the force of a nucleus, the photon materializes into electron and positron. The conversion of a photon to positron and an electron is known as the pair production. The reverse of pair production is also there, that is known as pair annihilation. The pair production is a phenomena that also cannot be explained on the basis of classical mechanics. Moving on to another limitation, that is, classical mechanics also unable to provide an explanation to Compton scattering. The Compton scattering is the scattering of X-rays by electrons present on the surface of non-metals like carbon. When X-rays of definite wavelength fall on the carbon, the non-metal surface, the X-rays will get scattered by electrons present on the surface of the non-metal. It should be noted that the scattered X-rays have higher wavelength than that of the incident X-ray. Such a kind of scattering is known as Compton scattering. The Compton scattering cannot be explained on the basis of classical mechanics. Moving on to another limitation, that is the inability to provide an explanation to wave-particle duality. It should be noted that light is having wave character as well as particle character. According to de Broglie, matter also have wave and particle nature, that is dual nature. Such dual nature of matter cannot be explained on the basis of classical mechanics. This is another serious limitation. The last limitation of classical mechanics is the explanation to Zeeman effect and Stark effect. That is, Zeeman effect and Stark effect cannot be explained on the basis of the classical mechanics. What is meant by Zeeman effect? The splitting up of spectral lines under the influence of a magnetic field is termed as Zeeman effect, whereas the splitting up of the spectral lines under the influence of an electric field is termed as the Stark effect. These cannot be explained on the basis of classical mechanics. That means there are several limitations in explaining the microscopic phenomena based on classical mechanics. Now, need for quantum mechanics. Quantum mechanics was initially invented because classical mechanics provided no means to explain properties of atoms, electrons and electromagnetic radiation. Quantum particles can act as both the particle as well as wave. That is, quantum particles can have dual nature. Quantum mechanics uses the language of probability theory. And finally, quantization of energy is an important property of microscopic particles. That is, in quantum mechanics, the quantization of energy is an important part. Now, we can move on to a historical timeline in quantum mechanics. Let us take a brief look at the historical timeline, how quantum mechanics came about. By this scanning, we can at least get a general idea of how things proceeded towards quantum mechanics. First of all, in the year 1900, the major notable contribution came from Max Planck. Max Planck proposed that light with frequency nu is emitted in quantize the lumps of energy that come in integral multiples of the quantity h nu. The energy associated with a quantum is E is equal to S nu, where h is a constant that is numerically equal to 6.626 into 10 raised to minus 34 joule second, which is known as the Planck's constant. The full name of Max Planck is Max Carl Ernst Ludwig Planck, and he won Nobel Prize in the year 1918 owing to his contribution towards the explanation of energy of quantum. Now, in the year 1905, the major contribution to quantum mechanics came from Albert Einstein. Albert Einstein's work on the photoelectric effect, which deals with the absorption of light and emission of electrons from a material. Einstein explained the phenomenon of photoelectric effect based on quantum theory, which is previously proposed by Max Planck. Albert Einstein won Nobel Prize for Physics in the year 1921 for his service to theoretical physics and especially for the discovery of the law governing the explanation of photoelectric effect. In the year 1913, Niels Bohr stated that electrons in an atom have wave-like properties. This correctly explained a few things about the hydrogen. In particular, the quantized energy levels which are present in hydrogen. Niels Bohr, the correct name Niels Henrik David Bohr, also won Nobel Prize in the year 1922 for his service in the investigation of the structure of atoms and the radiation emanating from such atoms. In the year 1924, an important contribution towards quantum mechanics was obtained from Louis de Broglie. Louis de Broglie proposed that all particles are associated with waves. That is, every particles have wave character also. This is simply known as the wave-particle duality. And this suggestion led to the formation of an important relation called de Broglie relation, which is lambda is equal to h by mv. The wavelength lambda associated with a particle of mass m traveling with a velocity v can be calculated by using the equation lambda is equal to s by mv. Here h represents the Planck's constant. Its numerical value is 6.626 into 10 raised to minus 34 joule second. The full name of Louis de Broglie is somewhat long, and the full name is Prince Louis Victor Pierre Raymond de Broglie. He won the Nobel Prize for Physics in the year 1929 for his discovery of the wave nature of electrons. A notable contribution came to quantum mechanics in the year 1925, and this contribution is from Werner Heisenberg. Werner Heisenberg formulated a version of quantum mechanics that made use of matrix mechanics. That is, Werner Heisenberg invented or introduced a new branch, that is matrix mechanics. Werner Carl Heisenberg also won Nobel Prize for Physics in the year 1932 for the creation of quantum mechanics. In the year 1926, Erwin Schrödinger formulated a version of quantum mechanics that was based on waves, or such mechanics is simply known as the wave mechanics. In this period, he wrote down a wave equation which is the so-called Schrodinger wave equation or Schrodinger equation. That is simply noted as Hamiltonian psi is equal to energy psi. We will deal with such equations in coming slides and in later modules. Erwin Rudolf Joseph Alexander Schrodinger is his full name. He also won Nobel Prize for Physics in the year 1933 for the discovery of new productive forms of atomic theory. Later, in the same year 1926, Max Born correctly interpreted Schrodinger's wave as a probability amplitude. This is known as Born interpretation of wave function. That is an important, remarkable contribution towards quantum mechanics. This interpretation yields the probability of finding a particle at a given location. Max Born also won Nobel Prize for Physics in the year 1954 for his fundamental research in quantum mechanics, especially for his statistical interpretation of the wave function, namely the Born interpretation of the wave function. And in the year 1928, the major contribution is from Paul Dirac. Paul Dirac showed that Heisenberg's matrix mechanics and Schrodinger's wave mechanics, that is the versions from Heisenberg and Schrodinger, are equivalent. That means the two versions proposed by two scientists, Heisenberg and Schrodinger, led to same conclusions. This notable information proposed by Paul Dirac in the year 1928. Full name is Paul Adrien Maurice Dirac, and he shared a Nobel Prize in 1933 with Schrodinger for the discovery of new productive forms of atomic theory. That about a brief historical outline towards quantum mechanics. Now, we can move on to the black body radiation that we already just mentioned at the beginning of the module. That is, black body radiation is an important phenomena that cannot be explained on the basis of classical mechanics. Now we can move on to details of black body radiation and explanation based on quantum mechanics. A black body, as you know, a perfect absorber and a perfect emitter of all kind of electromagnetic radiations. All incident radiations are absorbed, and this black body emit different type of radiations, and the emitted radiations is a function of radiator's temperature, which means the radiation emitted from the black body depends on the temperature at which the black body is placed. When a black body is at uniform temperature, its emission has a characteristic frequency distribution that depends on the temperature. This temperature dependent emission is termed as the black body radiation. The black body radiation phenomena has several experimentally noted facts. Such facts are discussed here. The black body radiation or the black body radiation spectrum depends only on the temperature of the object. It does not depend on the type of the material. Moreover, as the temperature of an object increases, it emits more black body energy, that is shorter wavelength, at different wavelengths possible. The picture is a graphical representation of black body radiation spectrum. From this graph, it is clear that as the temperature of an object increases, the peak wavelength, the emission wavelength maxima of the black body spectrum shift towards shorter wavelength region. In this graph, the left hand side is the shorter wavelength region or high frequency region, and the right hand side is longer wavelength region or low frequency region. And these are three peaks recorded at temperature 4000 Kelvin, 5770 Kelvin, and finally at 7000 Kelvin. By considering the emission maxima of these three, we will get a clear idea that as the temperature increases, the emission maximum shifted towards shorter wavelength region. That is, there is a shift towards shorter wavelength region. This implies the fact that blue stars are more hotter than red stars. Now, explanation to black body radiation. First of all, the Rayleigh-Jeans law. Lord Rayleigh and J.H. Jeans developed an equation which explained black body radiation at low frequencies. This is Rayleigh-Jeans law, that is U nu T is equal to 8 pi nu square divided by C cube into KT. Here, U nu T is the electromagnetic energy density, nu is the frequency, K is the Boltzmann constant, its numerical value is 1.38 into 10 raised to minus 23 joule per Kelvin, and T is the absolute temperature. Clearly, C represents the velocity of light, that is C is equal to 3 into 10 raised to 8 meter per second. This Rayleigh-Jeans equation can explain the phenomenon of black body radiation, preferably at low frequencies, but it fails to explain black body radiation at higher frequencies. Now, inadequacies of classical mechanics in explaining the black body radiation. The energy distribution in black body radiation could not be explained by the application of classical mechanics completely. The correct expression, that is Planck's radiation law, was derived by Max Planck on the basis of quantum theory of radiation. Based on the Planck's radiation law, we can explain the black body radiation. And the Planck's radiation law as such came from the Planck's quantum theory of radiation. So we can move on to details of quantum theory of radiation. Planck's quantum theory of radiation. This is the first postulate of Planck's quantum theory of radiation. Radiant energy or radiation is emitted or absorbed not continuously but discontinuously in the form of small packets of energy called quanta. In the second postulate, the energy of quantum is mentioned. The energy of the quantum is directly proportional to the frequency, that is E proportional to nu. We can replace the proportionality by equal sign by introducing a constant, that is h, or we can write E is equal to h nu, where h is a constant called Planck's constant. This is the second postulate of Planck's quantum theory. The final postulate of Planck's quantum theory is this: a body can absorb or emit energy in terms of whole number multiples of quanta, that is E is equal to ns nu, where n is whole number 1, 2, 3, etc. This is known as the quantization of energy. By these three postulates, we can conclude about Planck's quantum theory of radiation. Based on this Planck's quantum theory, Max Planck derived another equation that is called the Planck's radiation law to explain black body radiation. Now we can move on to numericals based on Planck's quantum theory of radiation. Calculate the energy in electron volt of a photon of wavelength 4000 angstrom. That is, you are having a photon of wavelength 4000 angstrom. That is, in this problem, lambda is given as 4000 angstrom. 4000 angstrom. That is 4000 into 10 raised to minus 10 meter. That is 4 into 10 raised to minus 7 meter. This is the given wavelength. Now, we have to calculate the energy in unit of electron volt. First of all, we have to calculate the energy in joules. As per Max Planck's quantum theory, it is clear that energy is equal to h nu. But nu is equal to c by lambda. That is, energy can be represented as hc by lambda, where c is a constant called velocity of light. By substituting various values, we will get energy in joules. The different values are Planck's constant h is equal to 6.626 into 10 raised to minus 34 joule second. Velocity of light is 3 into 10 raised to 8 meter per second divided by wavelength, that is 4 into 10 raised to 7 meter. On simplifying this, we will get energy in joules. But the problem is to find out energy in electron volt. So, we have to keep the joule electron volt conversion. The conversion is 1 electron volt is equal to 1.602 into 10 raised to minus 19 joules. Therefore, to convert this joules into electron volt, we have to divide this quantity. We have to divide this quantity with 1.602 into 10 raised to minus 19. That is, energy in electron volt is equal to divide this quantity by 1.602 into 10 raised to minus 19 joules. That is 1.602 into 10 raised to minus 19 joules. On solving this, 10 to the power we can simplify, and this quantity, the final quantity, will be appeared as energy in unit of electron volt. On solving this, we will get the final value of energy as 3.10 electron volt. This you can try whenever you are dealing with this problem, whenever you are studying this part. Now, we can move on to the Planck's radiation law. I already mentioned that the existence of the Planck's radiation law is to provide an explanation to black body radiation. And this Planck's radiation law, as I already mentioned, came from Planck's quantum theory of radiation that we already discussed. An accurate description of black body radiation has been put forward by Max Planck. Planck considered that the energy exchange between radiation and matter must be discrete, not continuous. The electromagnetic energy density per unit frequency of the radiation, that is U nu T, can be calculated by Planck's radiation law. This expression is the Planck's radiation law. That is, U nu T, which is the electromagnetic energy density per unit frequency, is equal to U nu T is equal to 8 pi nu square by C cube into S nu divided by e raised to S nu by kt minus 1. This relation is the mathematical version of Planck's radiation law. And in this equation, you know, T represents absolute temperature, that is the temperature mentioned in the Kelvin scale. H is Planck's constant. Nu is the frequency. 8 and pi are constants. C represents velocity of light. This Planck's radiation law can very well explain the black body radiation spectrum at all frequencies. That is, the Planck's radiation law, which is having strong quantum mechanical interference, can explain the phenomenon of black body radiation. Thus, in this module, we learned about several important drawbacks of classical mechanics and a historical timeline in quantum mechanics, and finally dealt with the black body radiation and Planck's radiation law. That's all about this module. Thank you.